started this topic, this is another application of equality of diagonal or ESC. And this is the three-phase fault at one end of the transmission line. So this is our single machine equivalent bus system, and this fault is occurring at one end. That is, we are at the sending end of the bus. And this fault is actually the three-phase fault. And more specifically, this is temporary three-phase voltage. The last class we explained this terms. Then due to this, actually we said that the power transmitted to the infinite bus will be zero. Why? Because there will be a short circuit path from here to the ground, and all of the power will be returning back to the system again. So there will be no power transmitted to the infinite bus, to the road side. Okay. Then power angle curve corresponds to the horizontal axis. Means that if this is our power angle curve, so here we can see this P increases with respect to the delta value, right? And it gets the maximum at pi by 2. Then again it reduces. But whenever due to the fault power transmitted to the infinite bus is zero, that means that now our P line will be exactly horizontal like this. So this is for P. Then the third point, if P is zero, that means we have a non-zero Pm is still there, right? That's the constant. So Pm will be higher than P, right? So we will see some acceleration in the road. That means the machine accelerates. And due to that, the speed, kinetic energy, and the rotor angle, all of these will increase. And our assumption is that when the fault is clear, both lines are assumed to be intact. Then with this information, actually we observe three scenarios: the network before fault, during fault, and after fault. So we saw that network before fault is this case, where we can represent this reactances by only this single reactance, that is the transfer reactance. And here in this case, there will be some power transfer to the system, and that maximum power transfer to the system can be represented by this P1 max. That is for the before fault condition. It will be the E prime V divided by X eq before fault. Then the during fault case, there is a short circuit path, right? So all of the power and current will be returning back to the system. So there will be no power transfer to the infinite bus. That's why in this case the maximum power transfer to the infinite bus system is equal to 0. Then the network after fault. So when the fault is clear, both lines are assumed to be intact. So the network remains the same as before fault. So this case is exactly same as the before fault case. And here you can see the X equivalent of the transfer reactance for after fault condition and the before fault are exactly same. These two are exactly same. Okay. And that's why this P1 max and P3 max will also be the same. Same thing. During fault and after fault, we actually get the same power, same transfer reactance, same thing. So we actually completed up to this in the last class, and now this class will start. So do you have any question from the previous class from this course slides? From here to slide number 31. Now we will start from here, right? Application of ESC, and that is the three-phase fault at one end of the transmission line. Now with all the informations that we just gathered, we will now try to plot P versus delta, the power angle. Okay, that is our target. So how can we plot? Look, this A is our initial point. A is the initial point. So at the initial point, we know that we have the PM and PE all should be equal, because this is the initial point, means this is at the stable regime, right? And at that time, the mechanical power input from the turbine and the electric power output from the generator will be same, will be equal. And at that time, the rotor angle is denoted by delta. Okay. So if I write here at point A, so at A, our PM0 is equal to PE0. Today's class, how many of you actually want to concentrate this lecture? Because today you have one lab quiz, right? So maybe that's why the attendance is low. And also those who have joined, most of the students are actually reading the control system lab, right? Who want to actually concentrate in this class? Can you please raise your hand? So 1, 2, 3, 4, lots of students. Actually, the topic of this course is very much easy, right? And actually, I normally cover a few slides in this class. So this is point A, the initial operating point at point A. PM is equal to P, right? This will work. Then the rotor angle is here delta. And in this point, the rotor was operating at the stable state, right? That means what will be the rotor speed? It will be same as the synchronous speed, and that speed can be written as omega, which is actually the omega is synchronous speed. Okay. Then at point A, speed phase voltage fault has been occurred. This fault. So now, if suddenly there is any fault, what will be the case? From we are at A, and now a temporary three-phase voltage fault actually occurs in this system. So what will be the scenario? We know that due to the fault, what will be the power transmitted to the infinite bus? It is actually 0. 0 means the power angle curve corresponds to the horizontal axis, right? So that's why whenever there will be any fault, the power angle curve will jump from A to B, right? Because B point means here the PE is 0. The power transmitted to the infinite bus should be 0, right? So that's why due to the fault, we are seeing a jump from point A to point B. So this is our point A to B. So what is the information at point B? So at point B, our PE is 0, right? Obviously our PM 0 is higher than P, right? And in this case, our PM should be constant. We will not increase the PM because in this case we want to observe the system response due to the previous problem. So our PM should be constant. We will not increase or decrease the PM. So P is 0 here at point B, and PM is higher than P, and still it is at delta naught point. Okay. Now due to this condition, what will happen? If you think about the swing situation, the rotor will accelerate, right? Means that our rotor speed will be now higher than the omega. If this is the case, what will happen to the delta? Delta W will increase, right? Because delta is this thing, E delta over dt, that is equal to omega minus omega. So if this difference omega minus omega naught is positive at that time, delta will increase over the time. And if this difference is negative, that means the delta will decrease. That is the concept, right? So now omega is the rotor speed that is getting increased from this omega naught value, means that our delta will also increase. Okay. So delta increases means from this point, from the point B, across which side should we move? The right side or the left side? Right side. Because the right in the right side, the delta actually increases, right? Because delta increases too. So the next time will be from B to C. Let's say we are now at C. Okay. So at C, what is the delta? It is actually the delta 1. And now, as the fault is temporary, so at point C, let's assume that the fault is now cleared out. The fault is removed. Okay. Now there is no fault. So we are at C. At C, we have the delta 1. Okay. And now the fault is cleared out. If this is the case, which scenario will it be? Will it be before fault, during fault, or after fault? It will be the after fault case, right? And in the after fault case, what is the P3 max or E? This is exactly same as the before fault, right? So whenever the fault will be cleared out at point C, now after this moment, from here there will be a jump to the point E, to the power angle, right? Because now there will be some power transmitted to the infinite bus, and that power should be exactly equal to the before fault case. If this was the before fault case, at this point delta 1, what should be the value of P? It should be this, right? On the power angle curve. That's why at point C, from point C, whenever the fault actually clears out, it will jump to point E. Okay. Have you understood this thing?
Immediately jump back to the P curve.
Yeah, exactly. We will jump immediately to P, because look, this is actually not continuous, rather discrete. Because before fault, the power transmitted was not there, right? But during fault, it was completely zero. Whenever the fault clears out, again there will be some power, because both lines are assumed to be intact. So again there will be some power there. Okay. So I am drawing this thing in terms of the power. Okay. So this is actually the power, not the speed or the delta. If this was the case for speed, at that time the speed can be instantaneously jump from one place to another place. But this is about the power. Okay. So it can jump from this point to this point.
So the before fault power and after fault power they must be same. So shouldn't it jump to P? That's the power level.
Yeah, okay, right? Good question. So he is asking that our before fault power and after fault power should be the same, right? Same means this question is the before fault power was here, right? delta, right? So there is some Pmax. Pmax is not dependent on this delta, that will be fixed, but the P is will depend on the delta. If delta increases, so the power will also increase, right? Here you can see that already this delta takes a very large value. That's why in this case the P should be this, right? Because P means Pmax sin delta. Here you can see this is written the Pmax, not P, right? Because Pmax means this is independent of sin delta. So that's why this P3 max and P1 max both are exactly equal, because this is in terms of only the maximum power. But if you write only the P1, then it will be P1 max sin delta, right? And if delta changes, this P1 will also change. That's why there will be a jump from C to P. Have you understood this thing? Now let's come to the point E. At point E, still we are at delta 1. So what is the relationship between Pm and P, at point E? Or P is higher than Pm, right? And that means what will be the rotor speed? It will decrease, right? It will decrease because there will be deceleration. And it decreases means now there will be some deceleration, right? But before that, in the acceleration phase, we have covered some area, right? We have actually some kinetic energy has been stored. Can you say which area actually we have covered during the acceleration phase? Which area you can call the area by these points? A, B, C, actually this area, right? The area under this Pm curve and this P. In this area, the Pm is fixed and the P is 0. So this curve is rectangle or square box. This is the area A1. That is our accelerating area, right? Now we are at point E, and you can see that Pm is lower than Pm. So according to the swing equation, our rotor will now decelerate. That means the omega will decrease. Now can you say what will happen to this delta? Delta will increase or decrease?
So delta will increase.
Why it will increase? Exactly. Look, let's say previously this delta naught is fixed at 1500 rpm, and in this accelerating zone, let's say the omega has been increased up to 1800 rpm at point C. So at point E, it is also 1800 rpm. From this point, it actually starts to decrease. That means it is still higher than omega naught, right? So it will decrease like 1750, 1700, 1650 like this. But at that moment, still this omega is higher than omega. So the delta value will still increase, right? Increase means from this point E, what will be the next journey? Towards this F, towards F. Towards F, right? Because the delta increases means we have to go right side of this power equation. That's why the next journey will be from E to F, and it will follow this curve, right? This power equation curve, and it will come here at point F. Okay? At point F. Now, at point F, what will happen? At F. At F, this delta decreases and this omega decreases, and at point F, this omega will be exactly equal to this omega naught in here. Okay? That means it should be in the stable state again, right? But here again at point F, the Pm is still lower than P, right? So due to this relationship, the deceleration phase will be continued, right? That means this omega will still decrease from this omega naught term. Now this omega value actually falls under this omega naught, right? So what will happen to the delta now? now delta will increase, right? Because now omega is getting reduced than this omega naught value. So the difference between omega minus omega naught will be now negative. So that means this delta will now decrease. Okay, that will be the case. So delta decrease means
স্যার
from f. Yeah.
ও স্যার ওমেগা ডিক্রিজ করার জন্য কি ডেল্টার চেঞ্জ হয় নাকি ডেল্টার চেঞ্জের জন্য ওমেগার চেঞ্জ হয়?
So actually this delta is the change in delta depends on this difference. This is the case. And at point f, the omega becomes omega naught. Let's say it was in the accelerating phase, it was 1800 rpm. Now in the decelerating phase, it starts to decrease, and at point f, it is getting, let's say, 1500. Now it is equal to this. Okay, but here is still the PE is higher than PM. So according to the swimming equations, the deceleration phase will still continue, right? That's why this delta will still decrease further. That means 1400, 1300 like this. That means in these values, with these values, we are getting this difference negative, right? Because this is fixed at 1500 rpm. So that means 1400 minus 1500 will be minus 100 or minus 200 like this. So this difference will be negative. Means that our delta is actually decreasing over the time. Okay. So now delta decreases means after point F, what will be our next journey? It will be towards the point E. Okay. So it will come F to E like this. Okay. But in the decelerating phase, we have covered some area. So what is the decelerating area here? Can anyone say? What is the decelerating area? Actually, GE left this area, right? This area is the decelerating area. And according to the ESC method, this area A1 and area A2 should be equal. Okay. This F point will be such that all of our accelerating area will be exploited completely here in the deceleration area. Okay, and that's why at F this should be the case. Omega should be in omega naught. And after this F, we will not need to move forward, rather we will move backward. Okay, because this after this point F, what delta actually starts to decrease again. So it will come down. So this is our accelerating area A1, that is ABCD, and this is the decelerating area GEF, and both should be equal. Have you understood this concept? Any question? Right? Now, whatever I have actually discussed or I have said, all the things are written over here. You can read out these things by your own. So all the things are written over here. And then an important concept is critical clearing and what is that? So let's come here. So this is our delta max. Why? This is the maximum zone for this case, right? So this should be treated as delta max. This is delta 1 and the operating point was at delta 1. Now this is the accelerating area A1 and this is the decelerating area A2. Now in the last concept we determined the transient stability limit, right? At that time what did we do? We actually let's say this is our case. Let's say this was the case. This was the initial PM0 and there was a sudden increase of PM1, right? From PM0 to PM1. So due to this, we had this accelerating area ACB and that has been completely given back in the decelerating area, right? Then how did we calculate the transient stability limit? We increased this PM1 further, right? Because we still have some decelerating zone here, this side. We can use this decelerating zone if needed. That's why we increase this line. If we increase this line, then our accelerating region increases. So to cover up this region, we need to go forward like this. Okay. So like this way, if we completely take all the decelerating area like this case, this is the limiting case where this is the increase from PM0 to PM1 and this is the accelerating area. Okay, so to actually give back this accelerating area in the decelerating region, we need to take all of this area, right? From B up to B. See, this is the limiting case. Let's say this is 50 unit, and this is also 50 unit. Okay. If we increase it further, then it will be maybe 60 unit. At that time, we can give back all of the 60 unit in the decelerating area. Then our point will be beyond D. Beyond D means this is the unstable state, right? That's why this point is actually the limiting point, where actually the accelerating area has been given back to the decelerating area, and there is no decelerating area left. Yeah. There is no available decelerating area. This is the limiting case where actually we calculated the transient stability limit. Okay. Now we will use the same concept here. Okay. Now here our PM is fixed. We can increase or decrease the PM, right? But what can we control? What can we control? We can control the clearing time, fault clearing time. Okay. Let's say previously the fault was cleared out at point C. Let's say from B to C. Let's say this is equivalent to let's say 0.5 C. Okay. Let's say for example. Let's say in another case our fault clearing time is let's say 0.7 seconds. What does it mean? The fault will clear at a further point than this C, right? Now this C prime will be our fault clearing point, right? If this is the case, then from this C prime, then it will be the E prime, right? And at that time we will get this amount of accelerating area, right? This is higher than the previous case, right? So if the fault clearing time is higher, at that time we will get more accelerating area. Now this area should be given back in the accelerating area. That's why the F naught is here. This is equal to let's say this increased one. Okay. Now still we have some accelerating area left here, right? If needed, we can take this. So like this way, we will increase this point further by allowing the fault clearing time a bit larger. Okay. So like this way, if we approach to a higher fault clearing time, let's say 2 seconds. That means it will be here. The C point will be here, right? So this point will be, this area will be our accelerating area. Now this will be our E, and to actually give back this energy in the decelerating area, let's say we need to take all of this area. Now this is the limiting case, right? Because if we move further, then we can give back all of the accelerating energy to this decelerating area. There will still be some energy left, and at that time the point will go here. That will be the unstable region. Okay. So to be within the stable region, there should be some limit for the fault clearing time. Have you understood this thing? And this is called this, and as this is the angle, that is the representation of this x-axis. That's why this concept is called the critical clearing angle. Okay, this is called the critical clearing angle. Now look, let's say from this delta naught, now our fault is cleared at C, such that this is our accelerating energy now A1, and to give back this whole energy in the accelerating area, we need to use all of the available area A2. Okay. Now this is the limiting case. Okay. So now this angle, this fault clearing delta C. Okay. Now read out this statement. The critical clearing angle delta C is reached when any further increase in delta 1 causes area A2 is lower than area A1. What does it mean? If we increase this delta further, then this area A1 will be higher than this remaining area A2. That means that A2 can be equal to A1. Okay, our exciting energy can be given back completely in the decelerity. At that time, the system will be in the unstable state. So what will be your limiting value? This. At what point we will reach this value? We will reach it when any further increase in delta 1 causes area A2 is higher, less than area A1. Have you understood this statement? So this is our limiting case. This angle is what the critical clearing angle.
So can this critical clearing angle be more than pi by 2?
It can be. It can. Okay, so there is no limit. It can be. If you take this PF as smaller, then it can be more than pi by 2. Okay. It depends on the scenario. So there is no limit whether it can be lower than pi by 2 or it should be higher than pi by 2. There is no limit. Now, this is the concept of critical clearing angle, but how can we calculate that at critical? Again, we have to apply the same theory that we did in the last concept. We know that this is the limiting case. In this case, this area will be exactly equal to this overall area, right? So that is area A1 is equal to area A2. So what is area A1? A1 is the area under between these two terms. It is P equals to 0 and this is PM, right? That means we will take PM minus 0. That is PM minus 0 is 0. And the integration will be from delta 0 up to delta 1. And we know that this delta 1 is actually the delta C, the critical clearing angle. So delta 0 to delta C. This is area A1. And what is this area? This is the area under between these two terms. Is this, right? This is actually the PE and this is actually the PM, right?
Delta C to delta.
What is this P? This is the after fault case, right? That's why this P should be the P max, but we denoted this P max as P3 max. That is the third scenario or the after fault case. P3 max sin delta. So this is the P3 max sin delta minus this is the PM, that is constant, and the integration should be from delta C to delta max. Always this the last swing should be treated as delta max. This is the maximum swing that can be possible. Okay. So this is delta max. Now if you do the integration in both sides, finally you will get this thing. I am not showing you the integration in very very simple. Then solve this equation for delta C, you will get this thing. Cos delta C will be this thing. Okay. Then from this equation you can easily find this delta C as it will be cos inverse of this conventional area. Okay. Like this way you can calculate the critical clearing angle. Okay. Have you understood this thing? I think this is very much simple, right? Then another term is the critical clearing angle. Okay. So look here we have denoted this thing as critical clearing angle, but we know that this is corresponding to some amount of time, right? Fault clearing time. If the fault clearing time increases, this delta will also increase. If the fault clearing time decreases, the fault angle will also decrease, right? Or this point C will be here or here, depending on the fault clearing time. So now we will use this term and we will try to understand this. What is the delta? So this is the critical clearing time, okay, or the time to clear out the fault. That is the time in between this. This is represented in terms of delta angle, right? But how can we transfer or convert this delta into time? That is important. How? And we can calculate this critical clearing time only for this case. only for the case where power transfer is zero during fault. Here during the fault power transfer is zero. Only in this time an analytical solution for TC is possible. Whenever during the fault the power transmitted to the infinite bus is zero, at that time only we can solve the TC analytically. And if the power is non-zero during the fault, we can calculate this TC analytically. Why? That things will be discussed in the next case. Because in the next case we will discuss another type of fault that is occurring at the middle of the transmission line. Here in this case we will see that actually our power transmitted to the infinite bus during the fault is not completely zero. There is some non-zero value. Okay.
So after the deceleration, we come to the point E. So initially, before the fault, we were at point A. As we have already said, decelerated the particular area, then how we will go back to point A again.
So you are asking that. Okay. So let's say if I summarize, our journey is A to B. This is during fault. Then B to C. This is still in the during fault, right? Now at point C, the fault actually is zero. Then our journey is C to D. C to E. This is the after fault, right? Then E to F, right? Up to this much you have understood, right? So this is now we are in the third scenario for after fault. Now from F it will be here, right? Now if there isn't any fault because the fault is cleared completely, right? So now the swing will be like this. Okay. And what is our steady state point? Point A. So it will be swinging like this, okay, like back and forth. And if there is any damping, at some moment it will converge to point A again in the steady state. Okay.
Then for the next cycle, while we are moving from E to F, will the area will change because I don't know the ADE area is equal to
Okay. Very good question. I didn't answer it because this is a bit complex. Okay. He's
Sir,
asking
what's
that
his question?
there is no fault in the system, right?
Sir.
So whenever
Sir, can you repeat the question, please?
he's asking that whenever we are at F, at point F, right? So there is no fault here. So what will be the next journey? From F to E, okay, then after E, what should be our journey? Should we follow this path? Obviously no, because there is no fault, right? Rather we will use this line, right? This line we will come here. And in this journey, A, F, G, this will be now the new deceleration area, right? Because there is a large area here, right? That is the deceleration area. Now again, we have to cross this point here, right? And we have to somehow keep back this whole decelerating area in the accelerating phase, right? But we didn't have any proper or available area, right? So what will happen? This is your question, right? You have to understand the question. So what will be happening? Because after this step, our journey will be now in this area, like this. Like
Will it
come here.
swing back and forth?
Okay. So this will be the higher area, right? So what will happen? So it will come to this zero point. There is no other point that it can go. Then again it will come here. Okay. So it will be swinging between these 2 points, but there will be some decelerating energy stored in this side. And how to mitigate this problem? Obviously there will be some damping. If there is some damping, then at some moment the point will, our actually final point will converge to this point. Because this amount of decelerating area can be given by time. So there will be some decelerating energy stored in the system. And in this cycle it will be larger. Okay? And if you incorporate the damping, then at some moment it will come to point A. That is our previous initial operation.
Now the system will be unstable.
Actually not unstable because this is operating within this region. It is not going here. Okay? So it is still stable. We will say that as a stable or marginally stable. It is not unstable. Okay? But if we use damping, then it will be dually stable. That is the thing. So now the fault clearing time, the critical clearing time. I am saying that this TC can be solved analytically only when the P is completely zero giving the fault. If not, then we can solve it. We will see the other case in the next scenario. Okay. But in this scenario, our P is zero giving the fault. So we can calculate the TC analytically. So you do not need to worry about this TC for the time being. Okay. So how can we calculate? Okay. During fault, the swing equation becomes this. Why? Because there is no P. P becomes zero, right? So this is zero. Now you can write it like this. So this term has been taken in the right side. So it is d square delta over dt square pi f naught Pm over t. Okay. Now integrating both sides. So there are double derivative. So if you integrate it once, so there it will convert to the single derivative. That's why you can see this is the single derivative. Okay. And in this side, all the things are constant actually. Pm is constant, f naught, pi x, all are constant, right? So how you will integrate? You have to integrate it in terms of 1, right? Because there is, you can multiply this thing with 1, then 1 will be integrated in terms of dt. Okay? So if you integrate it, you will get pi f naught Pm over x, and there will be t for this integration. Okay? Now integrate it again. So this single derivative will be now converted to this scenario, because this is actually the delta minus delta naught. Okay? And here you will get t square, right? Here you will get the t square. Okay? Now this delta naught, sorry, this delta. Okay? Now we can replace this delta with this delta c. Okay? And at that time, this time will be t c. Okay? So this is the expression. This delta can take any term, this delta, but this delta naught is fixed at here, right? But this delta can take any term, as well as this t can take any term. So we are now saying that if this delta is delta c, so the time that is required to make this, that is actually tc, the critical clearing time. Okay, that's why if we replace this delta with delta c, we will replace this t as tc, and solve it. We will get tc as this. Look. Now delta c, not delta. This is delta c, the fixed value, because we know this delta c. Okay. So if you know this value, you can calculate this tc analytically. That is the case. Okay. This is actually the critical clearing time. Why actually do we need this critical clearing time? Because to actually design the relay. So actually relay can understand the time. It can understand the angle. So you will set the time there. Okay. You will set the critical clearing time there, so that relay can clear out the fault before that time. Okay, that's why you have to describe the relay in terms of the time. That's why this critical clearing time is given. Have you understood this thing?
What will relay?
Yeah.
What is the role of the relay?
Relay. Okay, so relay will disconnect this thing. Okay, because if your fault sustains over this critical clearing angle, then there will be problem, because the system will be unstable. Okay. So if the fault actually doesn't remove, okay, from the system within that time, then the relay will operate and it will close the system. Otherwise the system will go to the unstable system, that is the undesired case, because there will be many damage inside the components, right? So that's why it's better to turn off all the things. The relay will sense that okay, the fault is not clearing out within the time, so I can just turn off all the ROM. Okay, that is the thing. So in today's class, we have, so this is the end of this case. This case is the three-phase fault at one end of the transmission line, and actually what we will cover here, we tried to actually we drew this power angle curve, okay, and from there we calculated the limit, that is the critical clearing angle. Okay, so the limit for the fault clearing time. Also from there we actually calculated the critical clearing time. That is the. Now the next case is the three-phase fault away from the sending gate. Okay, so this is another application of case. Here, previously the fault was there, right? will happen? We will discuss it in the next class. This is our main case.